Here comes the sky.
Back to the physical pendulum, which we briefly touched on in the last unit. If we instead oscillate an extended object, so the different atoms of the object are different distances away from the pivot, now we have a physical pendulum. We won't study physical pendulums in depth, but you can see the properties of simple harmonic motion that a physical pendulum has. What property of simple harmonic motion are we going to illustrate here? With three identical pendulums, the amplitude does not matter. Doesn't affect the period. What is not simple harmonic motion? These motions repeat but are not simple harmonic motion. So let's look at them. We have a ball bouncing. Talked about this at the beginning of the lesson, some things to notice. The force is most certainly not directly proportional to displacement. The force is a constant, which is weight, until the ball strikes the floor, then the force becomes very high for a brief moment. The normal force. The equilibrium is not equal distances from the two endpoints of the oscillator. Look at the displacement versus time graph. That is definitely not a sine wave. Sine waves do not have sharp points like that graph at 1, 3, and 5 seconds. The displacement graph is actually a bunch of repeating parabolas. It's not a sine wave. Bounce different balls from different heights, and they do not have the same period. So does the period of bouncing ball depend on its amplitude? Yes. So a bouncing ball is not simple harmonic motion. Cart bouncing between walls. This is an animation of a cart that is simply bouncing between two walls. This is not simple harmonic motion because the force is not directly proportional to displacement. Look at this blue graph. There is no net force until the cart reaches the wall. Then the force is extremely high. It's not a line, so F and X are not directly proportional. The graph of displacement versus time is not a sine wave. This graph is just jagged lines. A large amplitude pendulum. It turns out that a pendulum is only simple harmonic motion if you keep the amplitude small, so less than 30 degrees. If the pendulum swings wider than that, then the pendulum does not have properties of simple harmonic motion. Look in the graph, see what the problem is. Look at this. All right. The tangential force is actually given by F equals mg sine theta, where theta is the angle of the pendulum from the vertical, so theta equals 0 is vertical. Just like the downhill force on an inclined plane. Because the force is mg sine theta, the graph of force versus angle curves is part of a sine curve. Then when we're looking at the blue graph between negative 30 and 30, the blue graph has a line through the origin, so a pendulum is simple harmonic motion only if we keep the angle small. So it's curved here until we get to negative 30 and positive 30, and then it curves again. If the angle is large, then we can't use t equals 2 pi square root L over g to find the period. And can't say that the period is independent of amplitude.